Yeah, when we look at this problem, whenever you see horizontal plane, you should immediately think, okay, everything is on the table. So you're looking at the top view. If you're looking at the top view, that reminds you you shouldn't have friction force on your free body diagram. That's a keyword. So let's look at this. Oops. Then we're looking for tension in the cord. So here, the cord is connected from point O to particle P. And we're also looking for the normal contact face on P. So what does that mean is we have two contact surface, A and B. So if this arm is moving, we want to find out it's particle A, particle P in contact with B or A. And the next we want to find out, I think here, I have a typo here. This is a force. Okay. Now we're going to use the 6-step approach we learned in chapter 4. All right, no other method. This is chapter 4. 4A, you must follow the 6-step approach. The same deal on your homework and for your future exams. So let's, step 1 and 2 are pretty easy. Set up the coordinates, set up free body diagram first for that particle, and then set up your coordinate system. Once again, this is a horizontal plane. That means our weight force is going into the page. That's why we don't have any weight force here. We only have two forces. One is a tension force from the cable, and another one is a normal force pointing to the particle. This guy is our particle P. So on the free body diagram, why I draw my normal force going up instead of going in the opposite direction? Can I draw my normal force pointing to the different direction? See this? What do I mean is, can I draw my free body diagram like this? Raise your hand if you think, yeah, we can draw a free body diagram like this or like this. Raise your hand, you agree. Okay. Okay, good. Just one. Raise your hand if you think, no, we can't. Okay. Why? Opposite direction. Going to opposite direction. But if the particle P is sitting on a slope or table, yes, we know normal force has to go opposite the weight force direction, right? But right now, we're looking at the top view. This is the top view. The particle P is sitting on the table inside of arm. How do we know the normal force is going up or down? Yes, so we don't know the direction of normal force. That's what this problem is looking for. We're looking for, is the normal force come from the surface A or surface B? So the direction of normal force is unknown. So both, either way, if you draw your normal force going up or going downwards, they're okay. But you have to stick with it, right? Since we have coordinate system set up, if you draw your normal force going up, that would be in the positive J direction. But if you draw your normal force going down, your normal force is going to be in negative J direction. But in this problem, we're going to just follow the first one. We're going to assume the normal force come from that would be surface B. That's why the normal force is going up. And make notes here, tell yourself the weight force is going into the page. because it's horizontal plane. Whenever you see horizontal plane, that should be alarm ringing. Alarm, alarm. This is a horizontal plane. No weight force on free body diagram. Instead of weight force is going into the page, so it doesn't show on your free body diagram. Okay, that's step 1 and 2. Step 3 is write all the forces in vector form. Forces in vector form. In our free body diagram, we only have 2 forces. Interesting. Yeah, if you look at this free body diagram, how come we only have 2 forces? Yeah, we know the friction, the weight force is going into the page. Let's say this problem should tell you this is frictionless. So we don't have any friction. We don't consider any friction here. Hey, you learned free body diagram from your statics class, right? And in statics, you're trying to balance all the forces. Can you balance the forces just with 2 forces? One on X and one on Y? Is that possible? Now what is going on here? Is this possible? Is this the right free body diagram? What happens if a force couldn't balance off themselves? Okay. So here's a reminder again. What's the title of this class? Dynamics. Yes, that's a key difference between dynamics and statics. In statics, you must have the counter forces to balance out to cancel out all the forces. Make sure your sum of forces equals 0 on X and Y direction. But this is a dynamic class, so we always have external. The sum of the forces are not equal to 0 because everything is moving. If you have things that is moving, you have external forces acting on the particle. So that's okay. If we only have 2 forces, it couldn't get balanced out themselves, because if the forces couldn't balance off themselves, you're going to have F equals ma, you're going to have acceleration. Okay, let's write out all the forces in vector form. Tension force, it's along the negative direction of I, that is negative Ti. Our normal force, it's along the positive direction of J. So it's positive Nj. Questions? Step 2 is coordinate system, which is right there, I and J. Okay, that's step 3. Questions on forces in vector form? Shouldn't be too bad. Now step 4 is acceleration in vector form. So we're looking at the acceleration of that particle. That's what we care about. So how to find acceleration of that particle? I gave you guys some hint last time. I said because this is also a moving reference frame problem from chapter 3. So we have an acceleration equation. We learned the equation from chapter 3. When you have a particle moving inside of a rigid body, that's the time we use the equation from chapter 3. AP equals, another point is AO. Remind you back here. O is a fixed point on that rigid body. That's a pinpoint on the rigid body. And particle P, it's a particle moving inside of the rigid body. So the relative position and relative speed, relative acceleration from P with respect to O is different, right? It's not a point fixed on the rigid body. it's a point moving inside of rigid body. That's why we can apply this equation. That's from chapter 3. If you don't remember this, you can make a notes. This is a chapter 3 equation. From this equation, we can put information we know. Of course, AP is unknown here. But what is the acceleration of AO? What is the acceleration at point O? Yeah, that's 0 because it's pinpoint over there. It couldn't move. What is the acceleration of AP/O relative? So that's a relative acceleration. How to find that AP/O relative? So whenever you see REL relative, you want to put yourself into the moving reference coordinate system. In this case, you want to put yourself on that rigid body, arm OAB. That's true. You want to put yourself here. And I want you to put yourself there and look at the particle P. What is the acceleration of particle P with respect to your position over there? 0. Why 0? Yes, R dot, it's a speed, how fast particle P is moving in respect to your position. R dot is constant. That's why R double dot, which is the acceleration of that particle with respect to your position, should be 0. Let's write it up. R double dot should be 0. So now we know. Let's go back here. This term is also 0. That's great. What is alpha? Do we know alpha? Alpha is angular acceleration. What is the angular acceleration for this problem? 0. Yeah, let's check here. Omega equals 5 radians per second, which is constant. That tells us alpha must be 0. Great. We have one more term that's 0. Here, omega are given. Vp/O, that's a relative speed of particle P with relative velocity of particle P with respect to point O. That's R dot. That's, we know that. And minus omega square Rp/O. Rp/O is just a position vector from pointing from O to P. All right, can you put everything inside of this equation? 0 plus 0 plus 0 plus 2 omega k cross product Vp/O, which is your R dot on what direction? R dot on positive I direction. That's how we set up our coordinate system. Plus 2 omega k. Oops. My bad. That's minus omega square Rp/O. Rp/O gonna be Rp/O. It's a vector starting from point O, pointing to point P. So that is a vector of R positive I, because we set up I is along this direction OP. So that is Ri. Okay. Now we should have, if you break out that cross product, Your AP can be written as a vector. AP can be written as something I plus something J. So we have I term and J term. So for your I term, you should get negative omega square R I plus 2 times omega R dot J. Oops. Okay, so far you should finish step 4. Find the vector form for acceleration. But here, I just want to introduce one more method. So here, one box here. So this is from chapter 3. We can use chapter 3 to find the expression for acceleration. We have another method, a different approach, but you also get the same result. We can also use chapter 2. The equation we learned, no, sorry, not chapter 2, that's chapter 1. The equation we learned from chapter 1 to solve what is acceleration. If we come back here in this plot, particle P is moving inside of something that is rotating. And we know omega, we know omega double dot, we know R dot, we know R double dot. Does that remind you something? What we learned in chapter 1? What are the 3 coordinate systems we learned in chapter 1? Remember the names? Michael? Yeah, path, polar, and Cartesian. Which would be easier to use to describe the motion of that particle? P. Would you use polar, path, or Cartesian coordinate system to find acceleration of particle P? Krista? Path. What's the equation for acceleration on the path? Okay. I think there's a rate change of speed instead of that acceleration. Do we know anything about rate change of speed? Okay. Yeah. Polar would be a better fit. Let's see if we can use polar to solve the acceleration for particle P. What is the equation for polar? Remember that equation? It's with a lot of double dots and dot. Check your notes. What's the acceleration under polar coordinate system? And also how to set up your coordinate system. Remember in polar we have E, theta, and ER. How to set up your polar coordinate system. If this is our particle P, what's the direction of your ER? What is the direction of your E theta hat? Okay, Bethany, can you tell me where's your E theta hat?
Well, ER would like point towards the origin O.
Can you use your finger to show me where should I draw my ER? Towards to the origin O. If this is our O, ER. How about E theta?
And that should be perpendicular to that facing increasing theta so up.
It's going up. Okay. Almost there. I think here I would change the direction of ER. ER should pointing from the origin towards the particle instead of from the particle pointing to the origin. So to set up your polar coordinate system, your ER should go this way. Or you can put this coordinate system at your origin. Maybe that's easier to look at. E theta, ER. So your ER should always pointing from the origin to the particle. Okay, so this is how we set up our polar coordinate system. And what is the equation under polar coordinate system? Equation for acceleration, Michael? Yeah, that's a very nasty equation. I couldn't remember this equation. This is my second time teaching this course. I still couldn't remember that equation. So I don't expect you to memorize that equation, but you need to at least have that equation on your sheet somewhere. You can always go back to look. Yeah, that's the equation. But do we know anything about, we have so many things here. What is R double dot? R double dot, we know R dot is constant, R double dot, it's 0. We're given R. What is theta dot? Do we know anything about theta dot? What is theta dot in this problem? Is it give what? Omega? Yeah, omega is angular velocity. Theta dot is how fast that theta angle is changing. That's angular velocity. So we know R, we know theta dot, and theta double dot is 0. Let's get rid of that. Okay, now we can put things we know. Negative R omega square, that is ER hat, plus 2 R dot omega E theta. Okay, now we're from chapter 1. We can also write out what is the vector form for our particle P in acceleration. Should we do a comparison? From chapter 3, this is the equation we end up with. Negative omega square Ri plus 2 omega R dot J. Now we come back, look at what we got from chapter 1. Hey, that's the same thing. The only difference is on the top here, we have I and J as the unit vectors. On the bottom here, we have R hat, ER hat, and E theta hat. But in this particular problem, what is the relationship between ER, E theta, and I and J? That's a coordinate system conversion. All right, let's look at how we set up our I and J, like that. And how we set up our R, E theta. That tells you that's I, J. What's the relationship between these two coordinate systems? They're equal, right? Both I and ER are pointing to the same direction. Both J and E theta are pointing to the same direction. Therefore, this AP can be also written as negative R omega square I plus 2r dot omega j. That's exactly what we have up there. So there are two different methods you can use. Either you can find acceleration from chapter 3 or chapter 1. No matter which one you choose, you end up with the same solution. Okay, any question here? I think that's a good review of chapter 1 and chapter 3. Okay, now we're done with step 4. Let's move on to step 5. Step 5, what is step 5? Ashley, what is step 5? Combine the equation, which equation? F equals ma, yes, combine F equals ma equation. And this, remember, this is a vector equation. So you want to put your vectors of forces and vector of accelerations into this equation. You have tension force plus normal force give you m times acceleration of particle p. Now we can substitute all the I and j's into this equation. Negative ti plus positive nj equals m times negative omega square r I plus 2 omega r dot j. That's your acceleration. Remember, this is a vector equation. We can break that vector equation to two scalar equations. The first scalar equation is on I direction. We should have negative t equals minus m r omega square. First equation. Second equation on j, we have n equals 2 m omega r dot. That's the second equation. All right, here m, mass is not given directly. Things given, we know, but we know the weight force. So mass can be written as the weight force divided by the gravitational acceleration g. And g equals, I think it's 31.2 or 32.1. 31.2 feet per second square. Is that right? I only know that g under SI unit, it's 9.81 meter per second square. Depends on which units is given for the problem. All right, now we have two scalar equations. We can solve up to two unknowns. From the first scalar equation, we're able to find tension force T. T equals m times r omega square. If you plug in all the numbers, you should end up with about 2.91 pounds force. From the second scalar equation, we can solve for normal force, which is 2 omega r dot m. If you plug in all the numbers, you get a negative 0.776 pound. Okay, now we solve the value of T and N. Can we write T and N in vector form? Since the forces are vectors, T equals 2.91 I, that's pound. N equals negative 0.776 J pound force. And this is your answer, solution for this problem. I have a question here. How to deal with that negative sign? We end up with normal force is negative. Yes, remember from the free body diagram here, we assume, this is assumed, that normal force going up, which means the normal force come from surface A. So we assume particle P is in contact with surface A. That's why normal force is going up. But the result, our N, is a negative number. That means our assumption here in step 1 is not correct. So in reality, you don't have to go back to change your free body diagram because free body diagram is assumption. But in your solution, you can mention in reality that normal force N should going down to the particle. That means the particle P is in contact with surface B. Okay. Now we're done with this problem. I want you to take 2 minutes, review what you did, and maybe tell me where it doesn't make sense. Since this is the second problem we did in chapter 4, I bet you may have confusions about some of the concepts. Review what you did and tell me where it doesn't make sense. Which part is very hard to understand? Ashley?
Would there be other times that we would use like the other coordinate systems in chapter 1, or is there?
Yeah, so there will be other examples. We're gonna have to use either path or Cartesian coordinate systems. Don't worry, the next example is gonna be a different coordinate system. Michael?
Positive J that direction of whatever coordinate system you set up, or you just can assume anything and it'll just work out in the end?
Since it's an assumed force, so it can be any direction. So it can be either positive J or negative J, or if everything is on I direction, it can be positive I or negative I. Taylor, any question? Anything you feel like hard to understand? No?
Just like the acceleration equation in chapter 3, just knowing like what parts you set up out of the
Okay.
diagram.
But yeah, now you know you cannot have, you can either use chapter 1 or chapter 3. Depends on how problem is set up to find out your acceleration equation. Ella?
I agree that the acceleration equation is the hardest part.
Okay. All right. Mm-hmm.
Will you be asking us to do one version or the other? Or can you choose?
Oh, you mean 2 different methods we talk about in step 4? Either way. Which way you find easier to use? I don't care which way you use. Any other questions before we move on to the next example? Mm-hmm.
Was alpha 0 just because it didn't have the values for alpha?
That's because, let's go back here. In the givens, right here. Because omega is constant. Omega and alpha is always related. If omega is constant, Alpha is constant too, because alpha equals omega dot. Right. Now let's look at next example. It's example on your book, page 207, example 4A14. So we have a car. The car is traveling with a speed of V on a roadway with a banked turn. Okay, what does that mean? With a banked turn. And here's a diagram to show you. This is the real end of that car, and this is the road surface. So apparently that road is not flat. It has an angle, theta. And we want to determine the speed V of the car for which no friction force is required to keep the car on the roadway. Right? Imagine if you have a slope, if you just put a car there, if there's no friction, that car is gonna sliding down. But here we're trying to find if the car has a speed going into the page, and that car should stay up in position without sliding down. So first, trying to understand what is going on here. So the car, these are the tires of the car is in contact with the surface, the ground. The motion of the car is going into the page or going out of the page. Look at this as the 3 dimension. This is just the front view, or the, that's called, see this front view. On the right side, we have a top view. So the car can move along the track. Either it's a, in this case, can be a circular track. Questions? What answer? Yeah, we don't. In this case, if we assume that it's going out of the page, it's traveling out of the page. Okay. Now we want to find speed with no friction forces required to keep the car on the roadway. At first sight, it looks like, okay, we haven't done anything like this. But hey, just apply the 6-step approach to this problem. The 6 steps, the first 2 is set up your free body diagram. Let's just start with follow the steps. Let's see how far we can go. Draw a free body diagram for this car. Then set up your coordinate system. So how many forces should be on your free body diagram? Hunter, how many forces on your free body diagram? Three forces. What's the first one you have there? Weight force is going down. What's another force? Normal force from the road, so that is perpendicular, vertical to the surface. That's N. What's another force you have? Force drag you towards to the center. What is that force? Yeah. Why do you have that force on your free body diagram? How many forces in your free body diagram besides these two?
There should be three after centrifugal because it says it with no friction force.
Yeah. So it says no friction force is required, so you shouldn't put friction force on your free body diagram. But if that's your car, that's the only two forces the car is experiencing: weight force and a normal force from the surface. Hunter mentioned there's a force should pointing to the center, that way down to the slope. That's only part of the weight force. That's just the projection of weight force along the slope. So that's not a force itself. So your free body diagram, you should only have two forces. Now let's jump to step 2, set up coordinate systems. If we look at this problem, on the right-hand side here, it's pretty nice. It already set up the coordinate system for us. Same here. ENET, what does that mean? Whenever you see ENET, you should think about what? Path coordinate system. All right, great. So here, looks like they already set up the path coordinate system for us. I have a question here. On this left diagram here, why we only have an EN and a J? Where's our ET? Yeah, so at that view, ET is pointing out of the page, out of the screen. So you don't see that on the diagram, but you can see ET on the top view. This is a path coordinate system. ET is always pointing to the motion of the particle. The car is moving in the circular path. In this case, the car is moving out of the screen. So ET is pointing to the motion of the car. EN is pointing to the center of the curvature. That makes sense. Okay, so let's set up our coordinate system here. We should have J and EN. Okay, oops, yep. Now let's look at step 3. Forces in vector form. We only have two forces, so that shouldn't be too bad. We have a